Okay. Good morning. Hello, everybody. We are going to start in a few minutes, in 2 or 3 minutes. Okay, good morning, good afternoon, everybody. Thank you for joining this webinar on Simba. We are going to see together the latest developments in Simba, and we are going to share with you an example of a script that we've built to calculate efficiency map of inverters. So again, thank you all for being here. My name is Emmanuel Rutovic, and I'm the co-founder and the main developer of Simba. I'm joined with Guillaume, who is my associate, and we work together on Simba. So we'll start today with a quick introduction. Then I'm going to show you the latest developments that we've released in the last months and the new one that we're working on. Then Guillaume is going to show you the model and the script to calculate efficiency map of inverters. And finally, we'll have time for a few questions, if any. We are using, I don't know if you're connected through Zoom, but if you are connected through Zoom, you can ask questions in the Q&A window. So feel free to ask questions at any time. Maybe we'll answer them during the webinar, or maybe we'll wait until the end, depending on the question. Also, if you want to chat, if you have any comments, feel free to use the features on both LinkedIn and on Zoom. I'm also connected through LinkedIn Live. I know some people are watching the stream, so you can also ask questions, I think, through LinkedIn Live. So if you don't know what is Simba and you don't know why you're here, just a quick recap. So what is Simba? Simba is a simulation software that we are developing, and the goal of Simba is to do powertrain simulation. And our main goal is to minimize the engineering time that is required to build better power converters. So this is our core design philosophy for everything with Simba. One of the key differences with Simba is basically there are two ways to use it. The first one is what you see here on the left. It's a graphical user interface. It's a Windows tool that you can use to build your model, run simulation, and look at results. The second way to use Simba is through a very advanced Python-based scripting interface. And with the combination of both, the graphical user interface and the scripting interface, we can achieve and we can develop a powerful design workflow. And we are going to show you one of them in a moment. So we released Simba almost 2 years ago now. So it's doing well. I'm very happy about it. We released Simba beginning of 2021, and since our initial release, we released 1, 2, 3, 4, 5, 6, 7 versions. So it's kind of aggressive. Simba is built on very modern technologies, so it's kind of easy for us to build new release and to add features. So we have this aggressive roadmap, and we release very frequently major releases, and it's not going to stop. It's going to actually accelerate because our team is increasing. So I'm going to share with you a few of the things that we developed recently and that we are working on. We released a few months ago 2208, and the main features, the main add-on of 2208 is the AC sweep. It was in beta, and we released the first version during this release. So what is the AC sweep? So this is Simba. If you don't know it, this is the graphical user interface of Simba. So what is the AC sweep? It's the tool that we can use to determine transfer function of power systems. And it works like that. You inject what we call a perturbation at any point in the system, and Simba can calculate the transfer function between this perturbation and any signals calculated by the solver. And we are very proud of the AC sweep because it's very fast, and I think it's quite robust, and it has been validated. So for instance, here we calculated the transfer function between the duty cycle of a buck converter and the output. Of course, it's a very simple example. It's just for demonstration purposes. And I can specify something like 200 points. I can run the simulation, and you see it takes 1 second or so. And I can look at the magnitude of the transfer function and the angle of the transfer function. So we can use that then to determine and to design our control loop, if any. So that's the first features that I wanted to show you. We have also added the capability to run interactive simulation. So you run a simulation, and while the simulation is progressing, you can change the model, the parameters of the model, and you can update the design. This is available at first only in the Python module. We'll add it to the user interface during the first semester of next year. We have also added a lot of new models, including multi-winding transformer model, controlled source, and others. Of course, you have the details of the new features on our website. 2 months after, we released 22.11, and the main feature of this release was the compatibility with the XML thermal library file format that many semiconductor manufacturers support and provide. This tool was built this format, the file format was built for a software called Plex a few years ago, but it actually performed well, and a lot of manufacturers supported it. So now it's kind of becoming a standard, and many simulation and power electronics tools support this format. So what do we have in this file format is the thermal description of a semiconductor. So I'm going to show you. I'm going now in the test bench tab of Simba. I'm going in the thermal data tab, and here we have a new button called import thermal library file. I can click here, and from here I can load a thermal library file. This is one from Wolfspeed, which is a wide gap semiconductor company. And inside this semiconductor manufacturer, we can see multiple things. We can first see the thermal impedance. So this is basically modeling the thermal behavior between the junction of the semiconductor and the case. Okay, and those data were read from the XML file. We have the conduction losses data. So what we have here is we have for multiple temperature, basically the voltage drop as a function of the current. So from that only, when the semiconductor is on, we can calculate the conduction losses just by calculating voltage, the power as a product of the voltage and the current. And we have also the support, the possibility to calculate turn on and turn off losses by using those tables. And what we have here is basically the losses in joule, so that happen at any switching event as a function of the current, the voltage, and the temperature. Again, all those data are provided by the manufacturer. The standard, the XML thermal library file standard supports many options, like the usage of custom tables, custom variables, formulas like here, and we are compatible with all of that. So there is no compatibility issue in this feature. And this feature allows to calculate the losses and therefore the efficiency of semiconductors and converters extremely accurately. We don't need a very detailed SPICE model. We can calculate the losses and the efficiencies and the temperatures just using ideal switch model, because the losses are calculated from those data. So when you have imported one of those tables, you can simply go in the design tab and assign to one of the semiconductor the thermal data that is selected, and that's all. Then you simply run the simulation, and we can look, for instance, at the junction temperature and in the diode and the IGBT. We can look at the losses, we can look at anything. So this is the support of XML thermal library file format. We have added new dead time control model to simulate the dead time basically that we apply at semiconductors. And we also added the capability to annotate design with text and shapes, you know, just to have a better communication, to have models that looks better. So this is really these have been released already. So now we are working on new features for the next release that we are going to release in a few weeks now, in 3 to 4 weeks, beginning of January. One of course, we cannot say everybody. There are some stuff that we keep as a surprise that can just tell that they are going to be good surprises. We have developed new nonlinear inductance model. It's what you see here. So basically, you can define an inductance where the inductance value is actually a function of the current. So we can simulate the saturation of the inductance. And this is a first step in our journey to get more advanced semiconductor models and machine models as well. We are also developing a big change in the solver of Simba by introducing multi-time step solvers. What does that mean? That means that you can have one simulation, but not all the devices in one simulation will be called at all the time step. Some devices, especially the control devices, can be called at a fixed step. And this is to model very accurately and also to accelerate the simulation of basically digital controller. So, so this will allow things like delays, RMS calculation, and also accelerate the simulation with C-code blocks and things like that. So this is a very major advance in the solver of Simba. At our first result, we are about a 15 to 20% speed improvement in the design that we simulate today, just by using that. So it's kind of a major step. Another big change that we'll have in Simba is basically we are going to ditch the current file. You know, when you use Simba, the data is saved in the .simba file. This is going to be that will become a legacy file support, and we will replace it by a new file format that we'll call .gsimba. And this file format is actually a JSON based format, so you can actually open it with a text editor. And the main advantage of that is it accelerates drastically the startup of Simba, the operations like saving a file, opening a files, and also it improves the compatibility with the parallelization of calculation when we use the Python module. So this is also a major advancement. And as I was saying, we also have a few surprises for you. So yeah, that's actually the update on the new developments in Simba. Now I will give the floor to Guillaume, and we are going to see a little bit more about how we can use Simba to calculate inverter efficiency map.
Yeah, thank you, Manu. So yeah, let me show you this ID here. So the ID is to evaluate losses of motor drive inverter, considering here a power switch reference with a constant case temperature and 4 different operating points. So the inverter and the PMSM and its current controlled in the DQ domain are modeled in Simba. And this model is run from a Python script for the different operating points, and which also makes possible to evaluate the influence of different decibels voltages, gauge temperature, or switching frequencies. So let me show you the model in Simba. Here we are. So you can recognize here our motor drive inverter, the motor model, and here the model of the control. In each power switch here, we've got thermal reference, which is a reference from a SIC from wall speed, which has been imported, as Manu told you, with an XML file. Here we are. This is this MOSFET with connection losses, switching energies for turn on or turn off, and of course, thermal impedance. So as you can note here, we only have the channel which has been taken into consideration. So why? Well, let me explain you this few details before presenting you the Python script directly. So as I said, the thermal data have been extracted from the WallSpeed website. And from this website, so we got actually a first XML file, which gives the channel characteristics. So here you can note here the characteristics of the connection loss. So here, which gives the voltage drop depending on the current. And we also have a second XML file here with the body diode characteristics. And here we've got the conduction characteristics of this body diode in reverse conduction mode. So here, the first thing we can note is that we've got some voltage drop for this body diode, which is quite high, around 2.5 volts for a junction temperature around 150 degrees. Whereas if we look at the voltage drop, okay, for the channel connection, this voltage drop is still below 3.5 or 3 volts for a current which is under 50 amps, which is our case actually. So here, maybe we can neglect this body diode because the contribution of this body diode is not very significant for this current range. Moreover, about the thermal behavior, it's important to note that these two mechanisms actually belong to the same chip. So there is only one thermal impedance. And actually, if you open these two XML files, you will be able to note that the thermal impedance are exactly the same in each XML files. So here again, there is if the electric conduction of the body diode can be neglected, there is no point in considering two components. And that's why in our Simba simulation file, this body diode was neglected, which is much simpler and also which makes a little bit faster the simulation time. The second point is about motor here. This is a very classical motor model of permanent magnet synchronous machine with a sinusoidal back EMF. So here we've got the equation of this model, and here in red are the model parameters which have to be specified by the user. So now let's have a look to our Python scripts. So I'm going to show you in a few seconds the whole Python script. And here we've got the simulations parameters that the user can set as he wants. For example, here the case temperature, okay, the gate resistance of the power switch, which will modify the losses, the switching energies, turn on and turn off, also the switching frequencies, but also the decibel voltage, and here all the data which will set the number of operating points and the range of the torque and the range of the speed. What is also important to note is that in this Python script, we use a parallel computing features with a special Python module. So let's have a look to the Python script now. So here, this is the part where the user can set all the simulation parameters. So these are the simulation parameters, and I have already described you. These are the parameters of the motor. And here we've got a few methods to run simulation and to show the heat map. And afterwards, we've got the main script to perform the cloud computing. So first of all, let's have a look to this Python script, and you will see that it's very simple with this kind of script to launch and to run different simulations in Simba. So here we collect all the components, all the device of the Simba simulation file that we want to parameter. That's to say the control here of the operating point, the inverter settings, such as the switching frequency, decibels voltage, and here the motor settings with the parameters. Here we just run the simulations, just 2 lines of code. And here we get the results, okay, and we store them in different tables actually. And this method is then launched in the main script, which uses a Python module to run this script using the parallel computing. And maybe Manu, you can say a few words about this feature and how we use it.
Yeah, sure. I mean, it's basically extremely easy. That's the point. Even if you first, if you don't know Python and you see this script, you will probably understand how it works. Python is kind of very easy. If you know MATLAB, you will learn Python, in a few hours. There is nothing really special. And even like advanced stuff like running calculation in parallels, it's very, very straightforward. There is no thing special to install. There is just the Simba module to install, and that's it. So this is like the beauty of using Python. If you want to do the same thing in other tools or like in MATLAB, it will be very complex to implement, but running 200 simulations in parallels in Python, it's extremely simple. You see in line 244, we create the pool. So that's the pool of job we want to run. And in line 245, we actually run the pool with the different arguments. And the TQDM, maybe it's not very clear, but this is just to have the progress bar that you see below that shows the progress of the simulation. So it's very straightforward.
Yeah, thank you, man. So
and one last thing is still about Python, because we realize that sometimes engineers are a little bit afraid of jumping with Python. If it's the case, we can very easily, schedule a 1 to 2 hours session with you. So we can help you to install Python, to run scripts, and you will see it's very straightforward.
Yeah, this is the kind of things we have already done in the past. So yeah, it's definitely possible. Yeah, so thank you, Manny, for these comments. So if I go back to the slide, here are the results of some simulation that Manu has realized. So on his computer, the total runtime was about 5 minutes for 250 Ks for each simulation, which is quite fast actually. On computers which are a little bit slower, such as mine, sometimes it's a little bit it's a little bit longer, but anyway, it's always around 20, 30, 40 minutes. So this question of there is no value question of time. You don't need several days to build your efficiency map. So Here, this kind of example we can get, for example, here, we've got this efficiency map for switching frequency of 50 kilohertz with DC voltage bursts for 400 volts in the cage temperature of 80 degrees. And here is the entrance of different parameters. So you can see here decrease of the efficiency map if we increased the decibels voltage. But here we can reach different operating points in terms of speed, because here we have increased the decibels voltage, and here is the influence of the cage temperature. So here again we can see that the efficiency has a little bit decreased, and the same with the effect of the switching frequency. Oh, sorry, here the efficiency has increased because the cage temperature is a little bit lower. So, and so this is the kind of example of customization you can do with your script and then realize to your feature. So the next step of this kind of evaluation we would like to do, we would like to model different modulation strategies so that we will be able to study the influence of them, and especially the space vector modulation, but also discontinuous modulation strategies, which can give some interesting gains in terms of efficiency for the drive inverter. But on the other hand, you have to pay attention about the losses in the motor drive. We'll also like to introduce older inverter topologies, and especially multi-level topologies, in order to get the influence on the efficiency once again of this inverter. Of course, we would like to in future improve the PMSM model, and especially to consider the iron losses, so that we'll be able, for example, to see the whole influence of the different modulation strategies, and especially this continuous one. Also, we would like to improve a little bit the thermal analysis, which will be able to give faster simulation time, and a little bit the same thing to use the stop state feature with the model of our permanent magnetic synchronization to improve once again this calculation time. Yeah, so that's all for the next steps. So Manu, if you want to conclude.
Okay, thanks a lot, Guillaume. There are just a few things that I want to add. Would you mind? Okay, I can. Would you mind to share the script again, please?
Yeah, sure.
Maybe I missed that part, but in the script we actually coded the MTPA and the flux weakening algorithm.
Oh yeah, that's right. This is in this method, okay, which from the required operating points, okay, computes the required current in D axis and Q axis to get the right torque, and that's all.
And this is very good because it gives you, if you show again the efficiency map, the slide with the efficiency map, it gives you the area of where the inverter, actually where the drive can be used in terms of speed and torque using the flux weakening algorithm. So
yeah, and especially for example here, you can see the interest of increasing the decibels voltage from this phase on the left to this phase on the bottom here. As we increase the decibels voltage, so we can reach operating points with higher torque and a higher frequency. And yeah, sorry.
Sorry for the background noise. I think Junior was driving his car. Okay. Yeah, who is in a car right now? Okay, so thank you very much. And one last thing, which is very important, is in Simba we like to put everything in the open. We don't like to hide stuff. So if you go on our GitHub page and our repository that's called Simba Python examples, both the models and the scripts are actually available. It's not in the main branch, it's in our dev branch, because we usually put there in the dev, and then we when it's validated, we put that in the main. So if you go in the dev branch here, there is a folder called Inverter Efficiency Map. And here, actually, you will find the scripts that Guillaume just shown you. So if you're interested, you can have a look. You can download it. You can also get a trial version of Simba if you want to run that script. And you will find in the same repository a lot of very simple scripts that you can check to learn how we can run simulations, get results, play with our results, and so on. So I was sharing my screen, right?
Yeah. We have two questions from Vishal and Vishal. Yeah, Vishal is asking if if it's possible to evaluate the descending pole loss of the flying capacitor in the inverter. Yeah, it is, because we've got a resistance which can which can model your losses. And I'm looking for this resistance.
So the answer is, yeah, we have. Yeah. So the answer is yes, we can. It requires just a little bit of modeling parts, because probably you will have to first calculate. It depends what you want to do. If you want to have the temperature that varies as a function of the, to take into account the dynamics of the temperature in the losses, or if you want just to run multiple simulations at different ambient temperature and see the influence of the losses. But both are possible. It just requires a little bit of modeling part, and probably to use controlled resistor where the resistance is calculated as a function of the temperature, but it's possible to do.
Yeah, so here you can see my screen. We've got a restore, sorry, here, which provides thermal losses, and you can see on this restore here we've got a thermal pin, so you can connect this flying capacity, this your for example equivalent serial resistance of your flying capacitor with this model to a thermal model of your capacitor.
So thank you, Guillaume. Another question from Vishal. Do we have a device, metal oxide varistor? Do we have metal oxide varistor in the library? Actually, we have controlled resistor. So varistor are basically resistors that are function of the currents, right? So you can use the control resistor to write equations, of the resistance, and inject that in the model. So the answer is yes, but you have to write down the equation of the controlled resistor. Thank you, Vishal. Question from Jaime. Sorry if I misspell your name, but I think it's Jaime. Regarding the next updates on the semiconductor component library, do you plan to add new elements like GTO or TRIAC? Or will you extend the features and simulation capabilities or currently available components for now? Okay, so the first thing is the roadmap of Simba is kind of defined by the user needs. We have like very regular meetings with users to get feedback, to understand what they want to do, and we tune the roadmap for those. To be honest, we did not get any requests to get GTO or TRIAC in the library. But if it's something that you need, you can talk to us, and this is very simple. There is nothing really, complex to do regarding this. So if you need those and you're interested, let us know, and we can develop that. It's not a big issue, but we'll have to discuss together. The big work that we'll have for semiconductors that is planned and that is actually already started is to have detailed switching transient semiconductors model. So model where we can see exactly the waveforms during a switching transient, something quite similar that what you use SPICE for usually. So this is a big work. The solver of Simba is totally capable of doing that because we are very good to handle discontinuities and we are very good to handle variable time step. However, the model is a big subject. How to first, what model to use, and then how do we get the model from data sheets or from other SPICE model that the manufacturer could define. So this is something that we're currently working on. So that answers your questions. Question for you, maybe, Guillaume, question from Madi. SPVM, SVPWM.
Yeah, it's possible to model older modulation strategies, as I told you. We would like to do it ourselves for in our support team, but it's already possible thanks to the C code component in Simba. Let me show you. Yeah, let me show you here. For example, here. Sorry, code. Yeah, this one. So in this component, you're able to implement your own modulation strategy. Here in this function, you can do what you want, and that's what we plan to do to model this modulation strategies. But if you already know this modulation strategy, you can already code them on your own with this component. Yeah.
So question, thank you, Guillaume. Question from Paul. Can you use a lookup table to model the varistor characteristic? Yes, you can do. You can use a control resistor. Oh, do I share my screen? We always bouncing. So you can use a control resistor, and here you can use something that we call piecewise linear here, and that will model your lookup table. And from here you can type your lookup table, and that will control your resistor. So definitely we can do that. Question from Tolga. Do you have 3D model of efficiency according to frequency and temperature? So two things here. First, the thermal data that we get from manufacturer is actually more than 3D. It can be function of the gate resistance, it can be function of the temperature, it can be function of anything. So this is the data that we get from manufacturer. Then our scripts today calculate the efficiency for every torque and speed point that we provide. But if we want to add another variable that will be the temperature and make a 3D plot out of it, it's definitely possible. It's not in the script that you will find on our website, but we can change it to do it. And if you want, if you're interested, you can download the scripts and modify it yourself to do those 3D 3D graph. And if you need help, just let us know. No problem. I'll be pleased to assist you with that. Question from Javed. You want to take it, Guillaume?
The Simba makes use of physical properties, size, material properties of semiconductor devices for efficiency mapping calculation. It depends. That you mean for during the simulation for the simulation of the electrical waveforms, or to take into account the losses? Because it depends for the losses. So as we showed you, the thermal data of the power switches are modeled with tables. Let me show you this one. Okay, so here the component in each power switch. Here we've got the path or the name of the thermal data description here, which corresponds to a SiC MOSFET from Wolfspeed. And this thermal data is provided in the testbed tab, thermal data, and here we've got this component, and here we've got the conduction loss data, the turn-on loss data, and the turn-off loss data. So that's the way we model the component, and from this data tables and from the electrical currents and voltage which are switched, and from this data from the tables, we are able to extract the losses during the simulation, and these losses are then sent in the thermal model, and which makes possible to compute the junction temperature of the device. I hope it answers to your questions.
Awesome. So I think we have answered all the questions that we had. So that, I believe, concludes our, I'm sharing, right? Huh?
Yeah.
I believe concludes our webinar. So thank you a lot for all of you to have attended this webinar. I hope it was interesting. Feel free to go on our website. If you don't have Simba, you can actually create an account. It's free. If you are working in the academic world, you can get the license. It's entirely free. And if you are from a company, you can request a trial license. Of course, if you have any questions on the tools, or if you feel free to contact us, we'll be pleased to help. So thank you, and have a very good day, and I hope you will have time to enjoy your family during the coming holiday season. Have a good day, everybody. Yeah. Bye-bye. Thank you. Thank you, Guillaume.
Bye.
Bye-bye. Happy holidays, all of you.